Hi everyone, and welcome back to the channel. Gases are all around us, from the air we breathe to the steam coming off your morning coffee. And they all behave in predictable mathematical ways. In this video, we're going to dive deep into 4 foundational pillars that govern the physical properties of gases. First, we'll explore Boyle's law and learn about the inverse relationship between pressure and volume. Next up is Charles' law, which reveals how volume and temperature are connected. Then we'll move on to Avogadro's law and discover the role of moles and volume. And finally, we'll bring it all together with the powerhouse of them all, the ideal gas law, the single equation that can describe the state of an ideal gas under almost any condition. By the end of this video, you'll have the theoretical knowledge and the mathematical tools to predict how a gas will behave when you change its temperature, pressure, or volume. Boyle's law states that volume is inversely proportional to pressure. So we can say then volume is inversely proportional to pressure. And we can set this up as a formula. Volume 1 times pressure 1 is equal to volume 2 times pressure 2. For volume, we can measure in basically any volume unit, such as milliliters, liters, centimeters cubed, so on and so forth. All right, pressure. We can measure pressure in ATMs, which are called atmospheres, pascals, millimeters of mercury, kilopascals, torr, there's many other ones. Okay, a gas that strictly obeys Boyle's law is called an ideal gas, and they're more ideal at lower pressures. And one common use for Boyle's law is to predict the new volume of a gas when the pressure changes. If I were to graph an example of Boyle's law, where I have pressure and volume, it will give me points that make a hyperbola, which means then if the volume increases, then the pressure will decrease, or vice versa. You can do a separate or a different type of graph where I have volume and the reciprocal of the pressure. When you're graphing it this way, you get a straight line or a linear relationship. So you could use then y equals mx plus b here, because it's a linear regression. Okay, let's look at a sample problem. 500 milliliters of gas at 760 millimeters of mercury is compressed to 100 milliliters. So what is its new pressure? Okay, so we will say volume 1 times pressure 1 equals volume 2 times pressure 2. So our volume 1 is 500 milliliters. Multiply it times the pressure of 760 millimeters mercury. That's going to equal 100 milliliters times some other pressure. So let's divide both by 100. So pressure 2 is equal to 500 times 760 over 100. So my pressure 2 then is equal to 3,800 millimeters mercury, or you can say it's 5 atmospheres. I notice this because 760 millimeters mercury is equal to 1 atm, or 1 atmosphere. So that's something you kind of need to keep in your back pocket. So that's an example of Boyle's law. Charles's law says that volume is directly proportional to the temperature. So we could write our formula to say then that volume 1 is to temperature 1 as volume 2 is to temperature 2. If the volume increases, the temperature also will increase. Something to remember about Charles's law is the temperature must be in Kelvin. This is very important. So I would take my degrees Celsius, add 273 to it, and it will equal my temperature in Kelvin. Okay, if I were to graph this, we'll have volume in liters, and let's have our temperature in degrees Celsius. Okay, so my volume is 0, 1, 2, 3, and so on. Temperature is minus 300, minus 200, minus 100, 0. If I were to graph a few gases, for example, helium, methane, and water. There's something interesting that you might notice. If I were to extrapolate these until the volume is equal to 0, notice that all of these are all meeting at a certain place. This is at negative 273.15 or 0.2 degrees Celsius. This is called absolute zero. A simple problem with this would be if I have 2.5 liters of gas at 20 degrees Celsius, what is the volume when it's cooled to 0 degrees Celsius? Well, we'll say V1 is to T1 as V2 is to T2. We'll substitute there for the volume is 2.5 liters. The temperature is 20. So that would be 20 plus 273. The volume 2 is what we're looking for. The temperature 2 is 0 plus 273. So we would have 2.5 over 293 equals x over 273 cross multiplying, solving for x, I would get 2.5 times 273 divided by 293. So that gives me 2.33 liters. So always make sure that you convert those temperatures into Kelvin. Sometimes you'll see the combined gas law. The combined gas law is just simply a combination of Boyle's law and Charles's law just added together. So the formula will be V1 P1 over T1 equals V2 P2 over T2. So we're basically just combining both those together. Now, a lot of times you'll see something that's called STP. STP stands for standard temperature and pressure. The standard temperature is going to be 0 degrees Celsius or 273 Kelvin. All right, for pressure, okay, we can have several things here. We can have 1 atmosphere. We can have 760 millimeters mercury. We can have 760 torr. We can have 101.325 kilopascals, 101.325 pascals. Also, note that 1 mole of any gas at STP will be 22.4 liters. So in our sample problem here, we have an initial pressure of 12 atmospheres, initial volume of 23 liters, and an initial temperature of 200 Kelvin. After some change, the pressure is now 14 atmospheres, and the temperature is 300 Kelvin. So we're looking for what is the resultant volume. So we'll say V1 P1 over T1 equals V2 P2 over T2. So the original volume is 23 times the original pressure, which is 12. The original temperature is 200 Kelvin. I do not know the volume. The pressure is 14 atmospheres, and the temperature is 300 Kelvin. So we'll cross multiply. So when we cross multiply, we'll get 2800 V2s is equal to 82800. So our V2 will be equal to 29.6 liters. So that's an example of the combined gas law. Avogadro's law says that equal volumes of gases at the same temperature and pressure contain the same number of molecules. This relationship works best at low pressures. Okay, let's do a little simple problem here. Let's say we have carbon monoxide plus 2 hydrogens to produce CH3OH. Suppose I have 450 milliliters. Okay, let's say this. All at same pressure and temp. So if that's the case, I can look at a balanced equation. This is understood to be a 1 here. Understood to be a 1 here. Therefore, I would have 450 milliliters of this gas. And I have twice 450 for this one. This would be 900 milliliters. So Avogadro's law is fairly simple. If I were to combine Boyle's law, Charles' law, and Avogadro's law, we get the ideal gas law. This is the most useful of all of the formulas. Okay, so we'll call this one PV equals nRT. My kids affectionately call this PVNRT. Okay, we have some very specific units we have to use for this formula. Pressure can only be in atmospheres or kilopascals. If they're not, you have to convert them into these. Volume can only be in liters. N represents the number of moles. Of gas. R is a constant. I have two different constants. If I'm using atmospheres over here on the left, then this constant is going to be 0.0821. If I'm using kilopascals for my pressure, then it's going to be 8.314. Remember that the number of moles is equal to the grams of gas divided by its molar mass. We could write a similar formula that PV equals G over M RT, where G represents the grams of gas and M is the molar mass. So I'm going to say that PV equals G over M RT, cross multiply, so I have GRT equals PVM by both sides by RT. So G is equal to PVM over RT. So the mass is equal to, okay, at STP, I have 1 atmosphere. I'm going to use atmospheres here. The volume has to be in liters. So that's going to be 750 over 1,000. The molar mass of CH4, that's 12 plus 4 is 16. Since I'm using atmospheres, this will be 0.0821. And the temperature is going to be at 0 degrees Celsius or 273 Kelvin. So I can solve this. So G is equal to 0.535 grams. Okay, so let's practice working some of these. The first one, I have a gas at a pressure of 12 atmospheres, a volume of 23 liters, and a temperature of 200 Kelvin. If I raise the pressure to 14 atmospheres and increase the temperature to 300, what is the new volume? Well, if I see 2 volumes and 2 temperatures or 2 pressures, I know I'm going to be using the combined gas law. So I will say that V1 P1 over T1 equals V2 P2 over T2. So that's going to be 23 times 12 over 200 is equal to some volume. Pressure's 14, the temperature is 300. So I cross multiply. So 200 times 14 is 2,800 V2s. That will equal 82,800. Divide both sides by 2,800. So V2 then should equal 4. Let's see. Let me do that again. So that's divided by 29.6 liters. A gas has a volume of 4 liters at 50 degrees Celsius. What will its volume become at 100 degrees Celsius? Okay, so I have volume and temperature. So that's V1 over T1 equals V2 over T2. So that's 4 liters. The temperature is 50 plus 273. Okay, I'm looking for volume 2, and the temperature is 100 degrees Celsius. That means I have 4 over 323 equals V2 over 373. Cross multiply, so I have 323 V2s. Okay, so 4 times 373 is 1492. Divide both sides by 323. So my volume 2 then should be equal to 4.62 liters. So what pressure is required to contain 0.023 moles of nitrogen gas in a 4.2 liter container at a temperature of 20 degrees Celsius? Okay, so we'll use PV here. PV equals nRT. And I'm looking for the pressure. So I'm going to say that the pressure is equal to nRT divided by V. So the pressure is going to be, I have 0.023 moles, okay, times 0.0821. The temperature is 20 degrees. So that'll be 20 plus 273. That's 293 over the volume of 4.2 liters. So I'm going to multiply this out. I'm going to get 0.132 atmospheres. I'm collecting oxygen at a pressure of 123 kilopascals in a container that's 10 liters in volume. I'm looking for the temperature. I have 0.5 moles of the gas, and give my temperature in degrees Celsius. Okay, so we're going to say PV equals nRT again. I'm looking for temperature, so I'm going to divide both sides by nR. So I can say the temperature then is equal to PV over nR. So the temperature is equal to a pressure of 123 kPa times a volume of 10. I have 0.5 moles And I'm going to be using 8.314 because my pressure is in kPa's. So when I solve this, my temperature is going to be 295.89 Kelvin. But it says to give you temperature in degrees Celsius. So I'm going to subtract 273 from this. So that would give me 22.9 degrees Celsius. How many moles of chlorine gas would occupy a volume of 35.5 liters at a pressure of 100 kilopascals and a temperature of 100 degrees Celsius? So I'm looking for moles. All right, so PV equals nRT. I'm going to divide both sides by RT. So moles is equal to PV over RT. My pressure is 100 kilopascals. Volume is 35.5 liters. I had to use 8.314 because I'm using kPa's. And my temperature is 100 degrees Celsius. So that's 373. So plugging this in my calculator, I will get 1.14 moles of gas. What is the volume of a balloon if it contains 3.2 moles of helium gas at a temperature of 20 degrees Celsius and at standard pressure? So we're going to say PV equals nRT. I'm looking for volume, so I'm going to divide both sides by P. Volume is nRT over P. I have 3.2 moles. I'm going to use 0.0821. And I have our pressure in atmospheres. All right, temperature is 20 degrees Celsius. So that's 293. Divided by a pressure of 1 atm. So this would give me 76.98 liters. A 23.6 gram sample of unknown gas occupies a volume of 12 liters at standard temperature and pressure. So what's the molar mass of the gas? So I'm going to be using PV equals G over M RT. And I'm looking for M. So I'm going to cross multiply. So I have PVM equals GRT. Divide both sides by PV. So M equals GRT over PV. So M is equal to, I have 23.6 grams times R. I'm going to be using atmosphere, so I'm going to go 0.0821. All right, the temperature is standard temperature, that's 273. The pressure is 1 atmosphere. And the volume is 12 liters. So if I multiply this out, I should get 44.1 grams per mole. What mass of nitrous oxide is contained in 20-liter balloon at a pressure of 825 milliliters mercury at a temperature of 25 degrees Celsius? Okay, I'm looking for mass. Okay, we saw earlier that mass was equal to PVM over RT. So the pressure here is going to be 825 millimeters mercury, but I need to convert that into atmospheres or kPa, so I'm going to divide it by 760. So that will be my pressure in ATMs times my volume of 20 times my molar mass. Okay, so 2 times 14 plus 16, that's 44. 44 over 0.0821 times the temperature of 25. So that's 298. All right, so when I multiply this out, I get 1.09 times 20 times 44 over 0.0821 times 298. This is 955.3 over 24.47. So my grams will be equal to 39 grams. Okay, calculate the density of H2S gas at standard temperature and pressure. So density is equal to PM over RT. Standard pressure is 1 atmosphere. The molar mass, sulfur is 32.1 plus 2. That would be 34.1 over 0.0821 times the temperature of 273, because it's standard conditions. I get 1.52 grams per liter. And there you have it. From Boyle's law, showing a relationship between pressure and volume, to Charles's law, explaining the temperature's effect on volume, and Avogadro's law, linking moles and volume. We've seen how these fundamental principles combine into the incredibly powerful ideal gas law, PV equals nRT. Now you have the tools to analyze and predict their actions in the real world, whether you're inflating a tire or understanding atmospheric science. If this video helped, then please hit the like button and subscribe for more chemistry breakdowns. Thanks for watching, and I'll see you in the next lesson.